Okay, we are live today. What are we going to do today on Keenan Can Do? What we're going to do is first looks like turn down this mic a little bit, and then what we're going to do is continue working on learning C programming. So if we left off on chapter 4, if you remember from last time, we ran into a little bit of issues with the of all things the Emacs text editor, and I was setting up some stuff for GCC and using the Emacs compile mode. So we'll continue with chapter 4. Again, I am streaming this under a Creative Commons license attribution for this book, share alike license 3, so should be for fair use, and we'll get going. So we have compiling and debugging C. Let me know if the music is too loud. I'll turn it down as well. The GNU compiler, the GNU C compiler, GCC. A C program would typically consist of one or more files whose names end with .c. To compile foo.c, you can type gcc foo.c, assuming foo.c contains no errors. Agrarious enough to be detected by the extremely forgiving C compiler, this will produce a file named a.out that you can then execute by typing a.out within your folder. No errors. Extremely forgiving C compiler. So we'll have to find out exactly what that means later on. If you want to debug your program using GDB or give it a different name, you will need to use a longer command line. Here's one that compiles foo.c to foo. Run it using .foo and includes the information that GDP needs. GCC minus G3 out foo.c. Okay, so I'm assuming the switch minus G3. By default, GCC doesn't check everything that might be wrong with your program, but if you give it a few extra arguments, it will warn you about many, but not all, potential problems. GCC minus G3 dash wall dash out foo.c. Make. For complicated programs involving multiple source files, you are probably better off using make than calling GCC directly. Make is a rule-based expert system that figures out how to compile programs giving a little bit of information about their components. For example, if you have a file called foo.c, try typing make foo and see what happens. In general, you will probably want to write a make file which is named makefile or makefile and tells make how to compile programs in the same directory. Here's a typical makefile. Okay, let's try this just using make without having a file. Let's see how that works. So we have projects, C, chapter 2.c. Okay, so then if we do a compile, then we just do make, no target specified and no make found, file found. Okay. So make. Oh, I would just type make and then chapter 2. Oh, there we go. So you can do it without a make file as long as you target directly the file. Okay. Any line that starts with a sharp is a comment and is ignored by make. These lines are set variables that control make's default rules. We strongly recommend put negative G3 wall in your C flags. C flags. So these are C flags. GCC. Okay, so that's compiler. C compiler maybe. CC equals GCC. And then CF. C flags. Negative G3 and then space. So they're just separated by. Okay. So let's create one of these. It's just called makefile. Let's do makefile. And then we'll do, this is a comment line, I guess. Then we'll do CC equals GCC. We'll do C flags equal negative or -3 and -DALL. Okay. The next line is a dependency line. It says that if somebody types make all, make must first make hello world. By default, the left-hand side of the first dependency is what you get if you just type make with no arguments. By default, the left-hand side of the first dependency is what you get if you just type make with no arguments. Okay, so all, and I want chapter 2. Okay. So this is the dependency line. Dependency line. And then we have, how do we make hello world? The dependency line says you need to first make hello world.o and hello world and hello library.o. Hello world, hello world.o, hello library. Subsequent lines starting with a tab character give commands to execute. This command uses make built-in variables to avoid retyping and getting things wrong. Blank target hello world $@ equals target hello world $. Power equals dependencies hello world and hello library. So $CC $C flags minus, oh, okay. You can put whatever commands you want. Echo I just built hello world. Here we're saying that hello world O and hello library.o should be rebuilt whenever their corresponding source file. There are no commands attached to these dependency lines, so make will have to figure out how to do that somewhere else, probably from the built-in .co rule. Hello world.c, hello library, hello library, hello library. Command lines can do more than just build things. For example, make test will rebuild hello world if necessary and then run it. Test hello world underscore hello world. This lets you type make clean and get rid of anything you can rebuild. The $RM variable is defined to rm-r clean hello world. Given a make file, make looks at each dependency line and asks A, does the target on the left-hand side exist? And B, is it older than the files it depends on? Does the target on the left-hand side exist? And B, is it older than the files it depends on? If so, it looks for a set of commands for rebuilding the target after first rebuilding any of the files it depends on. The commands it runs will be underneath some dependency line where the target appears on the left-hand side. It has built-in rules for doing common tasks like building .o files, which contain machine code, from .c files, which contain C source code. If you have a fake target like all above, it will try to rebuild everything. All depends on, because there is no file named all, one hopes. So that's a fake target, okay. So all. Okay, I think that make is going to take a little bit more time to understand. Make really cares that the command line starts with a tab character. Tab looks like 8 spaces in Emacs and other editors, but it isn't the same thing. If you put 8 spaces in or a space in a tab, make will get horribly confused and give you an incomprehensible error message about a missing separator. This misfeature is so scary that I avoided using make for years because I didn't understand what was going on. Don't fall into that trap. Make really is good for you, especially if you ever need to recompile a huge program when only a few source files have changed. If you use GNU Make, note that beginning with version 3.78, GNU Make prints a message that hints at a possible space first tab problem like this. Make file, missing separator, did you mean tab? Instead of spaces, stop. If you need to repair a make file that uses spaces, one way of converting leading spaces into tabs is to use the unexpand program. Move make file to old unexpand make file. debugging tools. The standard debugger is GDB. Also useful is the memory error checker Valgrind. Below are some notes on debugging in general and using these programs in particular. Debugging in general. Basic method of all debugging. Know what your program is supposed to do. Detect when it doesn't. Fix it. Okay, so let's get this make down. So I don't have... Here we're saying... The next line is dependency line. How do we make it? Dependency line... The next line is... How do we make... The dependency line says you need to first make hello world and hello world. Oh, okay, so this is the fake. Okay, so all needs chapter 2, and then chapter 2 needs chapter 2.0, and then tab character, and then we have $CC $the flags -O, whoops, O, $at, $power, and then we can echo I just built chapter 2, hooray. Here we're saying a hello world should be rebuilt whenever corresponding. There are no commands. Okay. So okay, so this is the dependency line. This is the order of source, I guess. I don't know. I'm unsure what I'm really doing right now. I'm just going through it. Okay. So this then would be... This is the changes command. I don't know. Let's see. So I need chapter 2.0 when hello world... That's not... I don't have a hello world. When chapter 2.c changes. Okay. Command lines can do more than just build things. For example, we'll rebuild hello world if necessary and then run it. Okay. So make test. Build chapter 2. And then chapter 2. Okay, that's cool. You can get rid of anything you can rebuild. This lets you... Okay, so this is... kind of acts like a runner. I really need to learn the make commands in order to get real good at this. Okay. So then this clean... So that's a clean command. Okay, so these are targets, essentially. So that would be $RM... And then chapter 2. *O. Okay. So let's see what that does. Compile. Make. Compilation finished. I just built chapter 2, hooray. That's really cool. Okay, so let's do now... Let's make a change in chapter 2. Let's say we're going to count from... let's go to 15. Okay. Then we'll compile again. Let's do compile, make, test. Nice. That's pretty cool. Okay, cool. So I at least made one make file correctly, I guess. So definitely will want to revisit make stuff. So we'll do that. scenes. Need another scene so I could make notes. But I'll set that up tomorrow because I don't really know. Give me 1 second. I'm going to see if I can set up a scene here quickly. Let's call it note taking. Notes. Notes. Okay. And no, I want this stream. Okay. And then for notes, I need to... Oh, the scene though. Can I copy stuff? Hi, Aman. Hi. Can I copy those things? Copy. Then can I add them into this stream? Yes. Okay, that's cool. So let's see if I can set up this stream real quick. I'm just trying to I'm doing well. How are you? Thank you for joining the stream. I'm just trying to set up a scene where I could do some notes here. So I want to do I want to capture a window. Display capture. Window capture. Yes. We'll call it Evernote. Okay. And then it is in no, it is Evernote. There we go. What I'm doing well, thank you. And I want to make it kind of big like that, I guess. Then we'll make me a little bit bigger during that time. Okay, and I guess that would be it, right? Okay. So if I switch from, so okay, when I switch this, does it go back to the, does it go to the main with Emacs and the website? Someone tell me, chat. And then when I switch back, does it go to my my notes with Evernote? I think it does. Okay, cool. So let me make a new note. Not in inbox, it's in programming. No, it's move note to programming. Okay. C programming notes. I want things I want to revisit. I would like to revisit after videos. Let's take this to normal text, do a medium header. Let's say we want to revisit the make files, find a tutorial on GNU Make. Okay. So then when I go back to the YouTube stream, I should be back to there. Looks good? Okay. All right. Make gotchas, we got that. Okay, so the standard debugger is GDB, also useful as the memory error checker Valgrind. Below are some notes on debugging in general and using these programs in particular. Debugging in general. Basic method of all debugging. Know what your program is supposed to do, detect when it doesn't, fix it. I mean, that's pretty much it. Like that's what you do with debugging. Attempting mistake is to skip step 1 and just try randomly tweaking things until the program works. Better is to see what the program is doing internally so you can see exactly where and when it is going wrong. A second temptation is to attempt to intuit where things are going wrong by staring at the code or the program's output. Avoid this temptation as well. Let the computer tell you what it is really doing inside your program instead of guessing. Assertions. Every non-trivial C program should include assert.h, which gives you the assert macro. See Appendix B6 of K and R. The assert macro tests if a condition is true and halts your program with an error message if it isn't. Let's add it and then we'll look it up. So we'll go up here. We'll include assert.h. Okay. And then let's use the terminal, Windows terminal like we've had before. Terminal. You know, I might be able to actually add terminal. Yeah, you know what? Let's add terminal to our notes scene. So let's decrease the notes a little bit. Let's kind of go like that. Guess we'll kind of go like that, and then let's add a window capture terminal. Windows terminal. Yeah, yep. We got that, and then let's make this smaller. Wish we could. Yeah, that's fine. And then when it comes up, it goes over it. I guess I'm not really liking that. It doesn't really show the terminal either. Do it like that. Yeah, I don't want the terminal. Let's get rid of that. Remove. Okay, I'm removing the terminal. We're just going to use it like this. I'll just push it over that stuff when I'm using it. Okay, so let's go open Ubuntu again. Excuse me. Let's do man assert.7 info assert abort the program assertion false. Description: the macro can help programs find bugs in their program and handle exceptional cases via a crash that will produce limited debugging output. If expression is false. Attributes, interface, conforming to bugs. Okay, so attributes, assert, thread safety. Assertion value equals 0 failed. Okay. Void asserts scalar expression. Huh. Alright, let's see if we can use this then. Assert 2 plus 2 equals 5, return 0. Every non-trivial should include assert, which gives you macros. Assert. Okay, so let's just add an assert in here. Let's say we're going to assert that I is less than 12. Look at that. Compilation, assertion failed, I is less than 12. Okay. Line numbers and everything, even if you compile with the optimizer turned on, much nicer than mere segment. And if you run it under the debugger will stop exactly on line where the assert failed, so you can poke around and see why. Can you put a... But you're not able to like put in information in the assert, right? It doesn't let you. Error message to standard error and terminates the program. Includes the name of the file and function containing source code, line number of the call, and the text of the argument, something like. If the macro ndebug is defined at the moment was last included, the macro generates no code and hence is not recommended to buy it. If using a start to detect error conditions, software may behave non-deterministically. Okay. Full stack web developer. What stack do you use? Okay, let's see. Compiling run this program produces the following output. Why would you like to contact me personally? I'm just doing this for fun. Just streaming for fun. Line numbers. Okay, the GNU debugger. The standard debugger in Linux is called GDB. This lets you run your program under remote control so that you can stop it and see what is going on inside. You can also use DDD, which is a graphical front end for GDB. There is an extensive tutorial available for DDD, so we will concentrate on the command line interface to GDB here. Okay, let's add that tutorial. Tutorial for DDD. Let's copy it and we'll add it here. Okay. Warning, though GDB is rock solid when running on an actual Linux kernel, if you're running on a different underlying operating system like Windows, including Windows subsystem for Linux or OS X, it may not work as well. Either missing errors or should catch, or in some cases not starting at all. For OS X, you might also have better results using standard OS X debugger, LDB, which is similar enough to GDB to do everything GDB can do while being different enough that you will learn it on sub commands. Most IDs that support C also include debugging tools. Getting back to GDB, we'll look at a contrived example. Suppose you have the following program, bogus.c. Let's compile and run it. All right, let's write this program. So we'll do projects. We'll do bogus. Let's do chapter 4. We'll do bogus.c. Make directory. Okay. So we'll include our standard input.h. We're not including the cert. I thought we're gonna. So we're not doing the cert. Okay. So the comment is print the sum of integers. Okay. So this is supposed to print the sum of the integers from 1 to 1000. Bye. Thank you for stopping by. Subscribe if you like the content. Int. Ooh, that's going to be a problem. We can't just say int there. Oh, no. Int main. Int argc char. I don't want to do that, man. Void. Why is int on the same? Yeah, I think that was a typo, maybe. Int I, int sum equals 0, for I equals 0, 0, I is minus equal? Minus equal 1000. That doesn't make sense. I plus plus. I think that's where the error is. Oh, wrong screen. Yeah. Sorry. Oh, I have to remember because I set up 2 different scenes. So I can hit this and I can change the scene. So yeah. My bad. Can you see the code now? Okay. Sum plus equal 1. And then print f. I'm gonna do %d. And then sum. And then return 0. Oops. Okay, so now if we compile that, compile, make, let's just do GCC, minus G3, we'll do out, bogus, .c. Fatal error, no input files. Oh. Dun, 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 dun. I'm an idiot. Bogus. There we go. Compilation finished. We'll compile. Let's run it. Bogus. Bogus 687888264. Note that we include the G3 to tell the compiler to include debugging information. This allows GDP to translate machine address back into identifiers and line numbers in the original program for us. That doesn't look like the sum of 1 to 1000. So what went wrong? If we were clever, we might notice that the test in the for loop is using the mysterious minus equals operator instead of the less than or equal that we probably want. But let's suppose we're not so clever right now. It's 4 in the morning. We've been working on bogus C for 29 straight hours, and there's a negative equals up there because in our befuddled condition, we know in our bones that it's the right operator to use. We need somebody else to tell us that we are deluding ourselves. But nobody is around this time of night, so we'll have to see what we can get the computer to tell us. Or you can go to Amazon and you get yourself a little rubber ducky. One of these little rubber duckies. And you place this on your desk and you literally talk to it. So you say, rubber ducky, on line, whatever line it is, I want to go from I equals 0 to I minus equal 1000. And you're like, oh no. When you talk to your rubber ducky, when you tell it stuff that doesn't make sense, you're hearing it in your mind, and it kind of throws you into a situation where you can catch your errors. We actually in software engineering call that rubber ducking. So like if I go to my buddy and I have them walk through my code with them or whatever, I'll say, thanks for being my rubber duck. And we actually have rubber ducks on our desk. I don't have one because our house was recently cleaned. My desk was messed up, was cleaned, so I don't have a rubber ducky here, but I'll grab one. I have a few upstairs. I'll grab one on my next stream and show you guys the rubber ducky. All right, so that was a little tangent on rubber ducky. The first thing to do is fire up GDB, the debugger. We need somebody to tell us that we're deluding, but nobody is around this time of night, so we'll have to see what we can get the computer to tell us. The first thing to do is fire up GDB, the debugger. This runs our program in stop motion, letting us step through it at a piece at a time and watch what it is actually doing. In the example below, GDB is run from the command line. You can also run it directly from Emacs with mxgdb, which is the Emacs track to show you where your program is in the source file with a little arrow, or by running DDD, which wraps GDB in a graphical user interface. So far, we haven't learned anything. To see our program in action, we need to slow it down a bit. We'll stop it as soon as it enters main and step through it one line at a time while having it print out the values of the variables. So let's try it in Emacs because that's what we use. Let's do GDB. Okay. Okay, so current directory, licensed, this is a free software, there's no warranty, configured, type show configuration, or more bug. Okay, so break main, so we could go break main, breakpoint 1 at file bogus line 4, run. Oh, okay, cool. So we first breakpoint. Okay, here we're using break main to tell program to stop as soon as it enters main display to tell. Okay. All right, so okay, so run. Then we said display main display to tell it to show us the value of the variable I in sum whenever it stops, and N short for next to execute the program one line at a time. Okay, so display sum N display I N. Okay. N N N. Oh, I did 1, so that was right away. That's a problem. Okay. Yeah, when stepping through a program, GDP displays the line it will execute next as well as any variables you told it to display. Okay. When stepping through the program, GDP displays the line it will execute next. Okay, so let's read this from the top up. Here we're using break main, right here, to tell a program to stop as soon as it enters main display to tell it to show us the value of the variables I and sum whenever it stops, and N short for next to execute the program one line at a time. When stepping through a program, GDB displays the line it will execute next as well as any variables you've told it to display. This means that any changes you see in the variables are the result of the previous displayed line. Bearing this in mind, we see that I drops from 0 to 1000 the very first time we hit the top of the for loop and drops to 1999 the next time. So something bad is happening in the top of that for loop, and if we squint at it a while, we might begin to suspect that I minus equals 1000 is not the nice, simple test we might have hoped it was. My favorite GDB commands: help, get a description of GDB to commands, run, runs your program. Okay, so let's do help. Help. Aha. Aliases of other commands, breakpoints, data, files, internals, obscure, running, stack, status, support, trace points, user defined. Oh, that's cool. List of classes of commands. Okay. Quit, leave GDP, break, set a breakpoint, which is a place where GDP will automatically stop your program. Some examples: break, some function stops for executing the first line. Some function, break 117 stops for executing line 117. List, show part of your source file with line numbers handy for figuring out where to put breakpoints. For example, list some function, list all lines of some func dot list lines some func dot list some func. Oh, example is list space some func list all lines of some func. Period. Dash list 117 to 123 list lines 117 through 123. Next, evaluate the next line of the program, including completing any procedure calls in that line. Step, execute the next step of the program. If it contains no procedure calls, finish. Continue until you get out of the current procedure or hit a breakpoint, useful for getting out of something you stepped into. Continue until the end of program, a fatal error like segmentation or a bus error, or see a breakpoint. If you get a numeric argument, it will skip over that many breakpoints before stopping. Print the value of some expression. Print I, display. Like print, but runs automatically every time the program stops, useful for watching values that change often. Backtrace, show all the function calls on the stack with arguments, can be abbreviated as BT. Do BT full if you also want to see local variables in each function. Set disable randomization off. Not something you would need every day, but you should try this before running your program if it was producing segmentation faults outside of GDB, but not inside. Normally, the Linux kernel randomizes the position of bits of your program before running it to make its response to buffer overflow attacks less predictable. By default, GDB turns this off so that the behavior of your program is consistent from one execution to the next. But sometimes this means that a pointer that had been bad with address randomization, causing a segmentation fault, turns out not to be bad without. This option will restore the standard behavior even inside GDB and give you some hope of finding what went wrong. Okay, so that means that we can just do continue and we'll get done. All right, so we're done, and then is it quit? Is that what I heard it was? So we did quit. Let's get back to bogus C, and let's fix our program. Minus equals should be meta D should be I is less than or equal to 1000, and this should be I. Okay, and then we'll go that, and then let's do compile again, and then we'll do let's do cycle through. Oh no, it's okay, we can't cycle through. I was hoping we could cycle through. So we have GCC minus G3 O bogus, and then bogus dot O. Yeah, like that. No such file or directory. Bogus dot. Okay. I gotta practice that GCC stuff a little bit more. Oh, bogus to bogus C. Okay. Let's do that again then. Compile. And then we do GCC bogus bogus dot C. No. Oh, we have an error. So let's get to the error there. There we go. We had too many of those things. So there. Then we'll compile again. There we go. Yep. And then we'll compile, and then we'll run it, and we should get the correct information. 50-50. 500-500. That's it. Okay. So let's continue with debugging strategies. How many sections? Debugging strategies, common applications. Wow, this is a long chapter, isn't it? Yeah, I don't know if we're gonna get through this whole chapter today. But I'm glad that they're focusing on this stuff. In general, the ideal behind debugging is that a bad program starts out okay, but after executing for a while, it gets confused and starts misbehaving. If you can find the exact moment in its execution where it first starts acting up, you can see exactly what piece of code is causing the problem and have a reasonably good chance of being able to fix it. So a typical debugging strategy is to put in a breakpoint using break somewhere before the confusion hits. Instrument the program using display so that you can watch it getting confused, and step through it using next step or breakpoints, and continues until you find the point of failure. Sometimes this process requires restarting the program using run if you skip over this point without noticing it immediately. Yeah, that happens a lot. For large or long-running programs, it often makes sense to do binary search to find the point of failure. Put in a breakpoint somewhere, say on a function that is called many times or at the top of a major loop, and see what the state of the program is after going through the breakpoint 1,000 times using something like continue 1,000. If it hasn't gone off the rails yet, try restarting and going through 2,000 times. Eventually, you bracket the error as occurring, for example, somewhere between the 4,000th and 8,000th occurrence of the breakpoint. Now try stepping through 6,000 times. If the program is looking good, you know the error occurs somewhere between the 6,000 and 8,000th breaking point. Adding a dozen or so more experiments like this should be enough to isolate the bug to a specific line of code. The key to all debugging is knowing what your code is supposed to do. If you don't know this, then you can't tell the case where it is working from the case where it isn't. If you're confused about what your code is supposed to be doing, you need to figure out what exactly you want it to do. If you can figure that out, often it will be obvious what is going wrong. If it isn't obvious, you can always go back to GDB. This is very important. It's important to know what your code is supposed to do. So those copy and paste soldiers over there in the world, it behooves you to understand what your code is supposed to do and don't just copy and paste stuff. Or if you're going to copy and paste stuff, at least try to make an effort to understand what your code is supposed to do so that you can better have a chance of debugging if there's some errors later on. Common applications of GDB. Here are some typical classes of bugs and how to squish them with GDB. The same instructions usually work for DDD. Watching your program run. Compile your program with the -G3 flag. You can still run GDB if you don't do this, but it won't be able to show you variable names or source lines. Run GDB with GDB program name. Type break main to stop at the start of the main routine. Run your program with run arguments. The run command stands in for the program name. You can also redirect input as in the shell with run arguments file name. Oh, you can redirect the input as in the shell with the run arguments file name. When the program stops, you can display variables in the current function or expression involving these variables using display as in display x, display index of an array, display a expression. In DDT, double-clicking on a variable name will have the same effect. Use undisplay to get rid of any displays you don't want. To step through your program, use next. Always goes to the next line in the current function, not dropping down into function calls. Step, go to the next executed line, even if it is inside a called function. Finish, run until the current function returns, and continue run until the end of the program. This can be handy if you don't particularly know what's going on in your program and want to see. The same instructions. Watching your program run. I think this is a cool checklist that I want. Okay, so I've saved that in Evernote. So let's see. Programming. Yeah. There you go. Watching your program run. I like that. Okay. Dealing with failed assertions. Run the program as described above. When you hit the bad assert, you will stop several functions deep from where it actually happened. Run the program as described above. When you hit the bad assert, you will stop several functions deep from what actually happened. Use up to get up to the function that has the call to assert. Then use print or display to figure out what is going on. Example program. With GDP in action. Here we see that x has a value 3, which may or not be the right value, but certainly violates the insertion. Oh, okay, so let's do this. We'll do this dealing with failed assertions here. So this is, I guess failed assertion. We'll call it just failed assert. Failed.c. This will include a couple header files here. Standard input output at h. Include, it looks like standard library. .h. I don't even know what's in that yet. Include assert. .h, and then we do int main void. We'll do int x. Oops. X equals 3. Assert that x plus x equal 4. Oh, that's not gonna work. And return 0. Okay. And then let's compile this. Oops. Compile this. We'll do GCC minus G3. That's O. Let's do, what I call that? Failed dot C. Okay, the compilation worked. And then we'll do GDB failed. GDB. No, failed. Okay. So let's walk through how they do though. Okay, so they said, okay, run. Program received sig aborted. Signal raised in. Oh shoot, that's not good. Abort C. Raise C. Oh yeah, okay. Kernel faces call. Oh, okay, so this is raise. Alright, so I want to go up. I see. Up. Abort C. Up. Up again. Up. How many times I gotta go up? Aha. So that is in ours. Failed. Okay. Here we see that X has a value 3. Where do we see that? Oh, print X. Okay. Print X. Oh, cool. Yeah, I like how that's working then. That's really cool. Why do I have another? Oh, this is the window that the debugger is running on. Okay. I didn't know I was going to do a different window. Okay, here we see that X has a value 3. Which may or not be the right value, but certainly violates the assertion. Okay. Very much like the previous case, run GBT and the segmentation fault hits, then look around for something wrong. Curiously, GDP has no problem coming up with a value for, but I looks pretty suspicious. Okay. Alright, so we have a few more examples to go over. So this is now a segmentation fault. Okay. So let's do quit. Okay. And we'll do segfault.c. This one some more includes code.h include standard lib.h and include assert.h int main void int a 1000. I don't know what that is. Not quite sure what that is yet. I'm just typing this right now. I equals -1771724. Interesting. Print f the integer and then a new line, and then the value of ai, which should have been, oh, well, that's out of, I already know that's going to be out of bounds array, but I didn't know that was called a segmentation fault in C. So let's compile this. We're getting good experience with compiling now, huh? I'm just gonna do the whole thing because I want to practice. GCC minus G3 minus O, and we'll do segfault dot C. Okay, and then we'll do GDB segfault. Okay. So we'll run it. Inferior process exited normally. What? Why didn't it have a seg fault? Did I do 10,000 on that stupid thing? Oh man. 1,000. Int I 1771724 %D. File GCC G3 O segfault C. Compilation started. Okay, so GDB. Let's just do segfault. Run. Quit. Okay. GDB. Segfault. GDB. What? Quit. Okay. Hi, Prince. Sorry, I didn't just seeing your message. Why didn't I get a segfault though? Compile. Okay. GDB. Why is it on? You did not specify. Oh my god. Kill again. Yeah. Okay. Hi. Why no seg fault? I don't understand. 17717 int a int. I don't understand why. Int a 1000 int I. What if I do? Is it because the int is just not big enough? I don't know. Do that. Compile. Oh. Oh, I would have a seg fault. So why don't I have a seg fault now? What if I do? Is there a way to standard compile? Oh. Oh, small C99. Okay. Small C99. Okay. Now if I do GDB. No, this does not create a seg fault. Okay. Run GDB while dealing with infinite loops. Run GDB, wait a while. Hold on, I have to see if my wife is on the way home. We'll go for a little bit more if she's not. No, she's still at the hospital. I'm dealing with infinite loops. Run GDB. Wait a while, then hit Control C. This will stop GDB wherever it is. If you have an infinite loop, it's likely you will be in it, and that the index variables will be doing something surprising. Use display to keep an eye on them and do next a few times. Okay. Mysterious variable changes. Sometimes pointer botches don't manifest as good honest segmentation faults, but instead as mysterious changes to seemingly unrelated variables. You can catch these in the act using conditional breakpoints. The downside is that you can only put conditional breakpoints on particular lines. Here's a program that violates array bounds, which C doesn't detect. In the debugging session below, it takes a couple of attempts to catch the change in X before hitting the failed assertion. One thing to note is that a breakpoint stops before the line it is on executes. So when we hit the breakpoint on line 15, GDB, having observed that X is not equal to 5, is true. I has the value 0, but the damage happened in the previous interaction. Oh, in the previous iteration when I was -1. If we want to see exactly what happened, then we need to go back in time. We can't do this, but we could set an earlier breakpoint and run the program again. Okay, let's try this one. So this is mysterious. So we'll call it mystery. Mystery.c. And of course we're going to include standard input.h. Include standard lib.h. Include assert.h. And we'll do int main void. And we have a couple variables. We have an int x, int a, size 10, int I, and we'll set x equal to 5. And we'll do a for loop, I equals -1. I is less than 11. I plus plus. Then we'll set a of I, which isn't going to have a -1, equal to 37. I feel like I would catch these. I've been programming for a while. Assert x equal to 5 and return 0. Whoops. Alright. So I control save. We'll compile this. GCC. GCC minus G3. All out. Mystery. Let's see. Okay. And then let's debug it. GDB. Mystery. Okay. We'll run it. Program received sig abort. Aborted in kernel. GDB list main. List main. Okay. So what does list main do again? We do list. Okay. Let's do GDB help. Oh, help. Help list. Ten lines. Okay. Let's. All right. So we have x equals to do assert break 14. Ah, because there's the line. Break 14, and that's a conditional if x is not equal to 5. Breakpoint 1, file mystery, run. Yep. And then I could say display x is equals 37. And I Print A0. Aha, the weird number. Print A -1. 37. Print X. Print. One thing to note is the breakpoint stops where the line is on execute. So when we hit the breakpoint in line 15, GDP have observed that X was not equal to 5 is true. I has the value 0, but the damage happened in the previous interaction when I was -1. If we want to see exactly what happened, then we'd need to go back in time. We can't do this, but we could set an earlier breakpoint or run the program again. Oh. Let me understand what that was saying here for a quick. You know, the breakpoint stops when the line is on execute, so at the breakpoint at line 15. Damage happened in the previous interaction when I was -1. So on 13, set breakpoint 13. Oh, break. Print I. Huh. Very interesting. Okay. Okay, so we got through, I would say, half of the chapter and got some good practice on stuff using make, compilation. I might watch some videos tomorrow on learning some more compilation stuff. But we're going to end here tonight. And we'll pick up on Valgrind tomorrow. I'll set a schedule to start at 8:35, and I'll post it on the socials, so whoever wants to join, you'll get notification, and we'll pick up on chapter 4 starting with Valgrind. All right, I hope you guys had fun. Let me know in the comments if you like the content. Subscribe, and we'll see you next time on Keenan Can Do. Bye, everybody.